Hello friends, welcome back to You Can Do TV. Stories, 2 football fields wide, heavier than an aircraft carrier, sitting 80 miles off Louisiana, in water 1.5 miles deep. Things like this should not exist. The ocean keeps trying to tear them down. How do you build an entire steel city offshore, install it, and keep it running for 40 years? Stick around, the hardest part of the whole industry comes last. A 25,000-ton block of steel rose out of the North Sea in 9 seconds, the largest single offshore lift ever attempted by a ship built for exactly this. After 4 decades producing oil and gas, Brent Bravo reached the end of its service. 40 years ago, nobody had thought through how to take these apart. The decision: lift the topside in one piece, transport to shore, recycle 97%. Crews installed 6 concrete lifting points rather than welded ones. Diamond wire cutters severed the topside from its 150-meter base. Steel shear keys, 300 kilograms each, core drilled into the legs to hold it sideways against winter waves. Then pioneering spirit arrived. The world's largest construction vessel, twin hull, built for single lift removal. The ship ballasted down to slide its arms under. Tolerance against North Sea wind: 0.5 meter, 25,000 tons. The weight of a destroyer rose into the air in 9 seconds flat. A 72-hour clock started for installing navigation aids on the leg cups before any storm above force 8 arrived. If you have watched a piano go into an apartment and thought it nerve-wracking, this is the offshore version. The piano weighs a warship. The piano weighs a warship. The Brent platforms taught the industry how to take them apart. Appomattox shows how the next generation is built to last longer than anyone alive today. 16 stories high, 2 football fields wide, heavier than an aircraft carrier. Designed to sit 80 miles off Louisiana in water 1.5 miles deep. Lifespan: 40 years, double the usual. The power plant alone runs 150 megawatts, enough for 100,000 homes, fully electric to cut emissions by 25%. Engineers needed 2.5 million barrels of seawater a day for cooling equal to Houston's drinking water supply. So they drew it from 2,000 feet down, where the Gulf halves the requirement. The engineering looks excessive right up until you remember what it's built to argue with. Before any of this scale existed, somebody had to prove a platform could float at all. Auger was the first tension leg platform, 5,000 tons anchored in 2,800 feet of water in the Gulf of Mexico, held to the seabed by tendons under permanent tension. Before Auger, the industry believed nothing offshore was commercially viable past 1,000 feet. The platform floats on huge pontoons. The tendons keep it from drifting and pull it slightly downward, like a kite string in reverse. The platform became too big to assemble at sea. The next question was how to deliver one in one piece. At sea, you do not build a tower one floor at a time. You build the whole thing on land, then deliver it. A complete offshore platform splits into 2 pieces. The jacket, the steel space frame standing on the seabed, supporting everything above. The topside, the working part, production plant, accommodation, drilling rig, the part where people live and work for decades. A material barge brings the jacket to site first. A heavy lift crane swings it from horizontal to vertical, lowers it into the water during upending, sets it on the seabed. Foundation piles slide into each jacket leg, weld together end to end. Then, a hydraulic hammer drives them through the leg to target depth. Pile tops cut flush. Crown shims weld jacket to piles. Only then does the topside arrive, already complete, already wired, already plumbed. The crane lifts it off the transport vessel, swings it across, sets it onto the jacket within centimeters. Workers connect the internal systems between modules. The bottleneck is offshore time. Every hour at sea costs more than the same hour on land, and weather can shut everything down. The first move is leaving the yard with the building already complete. Before anything reaches the sea, it has to leave the yard, and a topside the size of an apartment block does not drive itself onto a barge. At a Middle Eastern fabrication yard, a complete 8,000-ton topside sat on the quayside, having absorbed over 2 million man-hours of work, piping 700 tons, electrical and instrumentation 846 tons, cable runs 91 kilometers, painted area 120,000 square meters, using 1,800 tons of paint. To move it onto a barge, self-propelled modular transporters slid underneath. Hundreds of hydraulic wheels lifted the structure together and rolled it forward centimeter by centimeter, while engineers in the control room balanced the barge's ballast tanks in real time to keep the load level as it crossed from quay onto deck. 8,000 tons does not move quickly. It moves carefully on wheels with a long safety briefing first, and lots of radio chatter throughout. For smaller platforms, the whole installation is done by one heavy lift crane on a derrick barge, and the precision is still measured in centimeters. The Larac wellhead platform installed off Sarawak in 80 to 90 meters of water, a 1,000-ton four-leg jacket on one barge, a 500-ton topside on another. The main crane side lifted the jacket, upended it vertical, set it on the seabed, 5 sections of 1.2-meter diameter pile, each up to 181 meters long, hammered through the legs to target depth. The derrick barges are too big to sail oceans on their own, so they travel by ship. Derrick barge 30 measures 128 meters long, 48 meters wide, weighs 24,500 tons. Its main crane has a 71.6-meter boom with a 2,794-ton capacity. To cross oceans, a heavy lift transport vessel ballasts down 23 meters until its deck is underwater. The barge floats over the submerged deck. Then the ship rises again, carrying the crane on its back. Even the equipment that lifts things needs lifting. For platforms too big for any crane on Earth, a different method takes over, and it borrows its principle from a tide. Off the coast of Vietnam, a complete topside sat on a barge between the open legs of an installed jacket. The crew pumped seawater into the barge's ballast tanks. The barge sank, and the topside transferred onto the jacket legs without ever being lifted by a crane. Gravity does the install, the barge just gets out of the way. The same idea scaled up off Abu Dhabi. The Lulu topside threaded into the jacket between sunset and sunrise. Tugs nudged the barge into the slot between jacket legs to within centimeters. Ballast water filled the tanks. The topside descended onto its mating points. By morning, the install was finished. The Bakor platform off Sarawak added a trick. Removing the mooring lines, the 11,500-ton POC-PPA. Topside floated to site on a transport vessel fitted with dynamic positioning. Computer-controlled thrusters held the ship steady inside the jacket slot. No anchors, no tow lines at all. The crew then ballasted the vessel down. The ship parked itself between two concrete legs, the way a self-parking car backs into a space. Only the car weighs 30,000 tons, and the parking lot is the Pacific Ocean. The mechanics of a float-over installation explain why offshore engineers are obsessed with ballast pumps. Off Mexico, the PB-A topside weighed 7,000 tons, sitting on a barge in 26 meters of water. To install it, tugs pushed the barge between the jacket's 8-pile cluster. 6 ballast pumps moved 1,350 cubic meters of seawater per hour to lower the barge in stages. The topside touched its mating points, the load transferred, and the barge continued sinking until it was free of the structure entirely. Total mating sequence, 16.25 hours of patient work. Barge removal afterward, 120 minutes total. To get the topside loaded out of the yard in the first place, 4-strand jacks pulled at 65 meters, with a combined force of 1,824 tons, holding the barge level for 6.5 hours straight. The maths behind making something this large move centimeters is frankly ridiculous in the best possible way. The record for a while belonged to Thailand. The Artha Central Processing Platform off Thailand made it a 17,000-ton integrated topside onto a 5,000-ton jacket in the Gulf of Thailand, at the time, the largest integrated deck installed anywhere in the Asia-Pacific region. Fabrication started in July 2005 at Batam Island, Indonesia. The whole build absorbed 6.8 million man-hours, without a single lost-time incident from start to finish. 6.8 million hours of work. Nobody hurt. Somebody was paying attention. At some scales, float-over alone is not enough. The deck has to arrive in pieces. For the Krishna Godavari D6 control and riser platform off India, the 18,100-ton ties was split in two and lifted onto the jacket as separate decks. North deck, 2,540 tons. South deck, 3,048 tons. The 8,200-ton jacket itself was built in Morgan City, Louisiana. Fabricated in 11 months, towed 13,375 nautical miles across the world. Launched and upended on the Indian seabed. Engineering in Houston. Construction engineering and topside fabrication in Dubai. The EPAC scope was delivered in 18 months from award. The lift solved one problem. The next is how anything stays in place once the weather actually shows up. The crane vessel goes home. From here on, the structure has to stand up on its own. A jack-up rig is a hull with 3 legs taller than most apartment buildings, and the only way to get one wet is the cheerful violence you see here. Push it sideways off the slipway and let physics finish. The P2037 Fortis, a PPL Pacific Class 400 from PPL Shipyard in Singapore, slides in. Tugs like Noble Ace catch what gravity already started. Sliding a rig into water is just the easy step. Making it stand up on its own legs is the engineering problem, and no builds jackups the way LEGO would if LEGO had hydraulic cylinders and 300-ton ambitions. The system has 2 halves: in-to-float pontoons, box-shaped floating elements you bolt together in water to form whatever footprint the job needs, and ion no-lift modules, 4 of them, driven by a pair of hydraulic cylinders. Total combined lifting capacity, 1,200 tons. The piles end in a spherical joint, so when the foot hits an uncooperative seabed and refuses to sit flat, the joint shrugs and finds its angle. Champagne for the launch, hydraulics for the work. All of that modular thinking has to prove itself at the dock before anyone trusts it offshore. Haven is a jackup built not for drilling, but for sleeping. 470 single cabins destined for the Ekofisk Center in the North Sea, where North Sea workers need somewhere that isn't slapped by waves. Before it goes anywhere near Ekofisk, It gets tested in Idehav near Arendal in Norway. The numbers are not at all subtle. Lifting height, 75 meters. Total structural weight, 20,000 tons. 20,000 tons. Haven then pulls itself free, slowly enough to make the whole thing look far easier than it really is. Equipment going up onto these jackups has its own delivery operation. Briggs and Envo crane, a green frame onto a tug, cross a port at night, and hand it up to MPI resolution. And the equipment doesn't fit in a van, it rolls. Drone footage from a Chinese fabrication yard catches self-propelled modular transporters crawling under an orange machine the size of a small building, ribbed, structural, vaguely science-fictional, and trailing a forest of cables. Behind it, a giant white drum the size of a small Ferris wheel rides on another SPMT. The two ride toward the quayside like very patient, very expensive elephants. An entire industrial yard rearranges itself around whichever vessel loads next. Not every leg holding up a platform is actually a leg. Offshore wind needs foundations too. And the elegant trick here is the suction bucket jacket. The jacket looks like a steel tripod with giant inverted cups at each foot. The vessel lowers it to the seabed. The cups land flat, and then the operators do something that sounds wrong. They pump the water out from inside the cups. The vacuum drags each bucket down through the mud until the jacket is locked in place. No piling hammer or underwater noise, just physics sucking a building into the ocean floor. Floating bridges trade legs for water. SR 520 across Lake Washington. 77 pontoons stitched into a road, K and L joined on February 17, 2015. Platforms above water are only half the job. The other half lives where no one photographs it. NDL's Gen 2 reel drive pulls polyester mooring rope under back tension from 15 storage reels and feeds it into the Gulf of Mexico. A mooring line keeps the platform from drifting. The riser does the actual work, fluid moves through it. On the Mero field off Brazil, MDL's FlexLay spread handled the job in ultra-deep water with zero margin for error. A 4-track tensioner gripped the riser, a reel drive fed it. A data assembly with 5 pigtails went down through the moon pool, and a fiber optic cable was laid alongside. The full spread was sized by a feed study before anyone approached a winch button. Everything that goes into the sea eventually has to come back out. Before the Balder FPSO could return to port for refurbishment, every production riser and control umbilical connecting it to the seabed had to be recovered without damaging them. An MDL spread one recovery system using a 4-track tensioner and a 3-meter 50-ton chute, gripped each flexible line as it rose through the moon pool and onto the deck, where crews cut it into 12-meter sections for transport. Getting equipment into the sea is difficult. Bringing it back intact is often even harder. The kit makes the spread, and the spread makes the operation. MDL's TTS 4 series tensioner with 85 tons of line pull. Single track opening in horizontal mode. Single track opening in horizontal mode gets crated alongside a 48.5-ton electric winch and shipped over to Brazil for FlexLay work in the Santos Basin. Watching a single yard crane drop both packages onto a lowboy trailer is an unusual sort of meditation on tonnage and patience. The reason this gear shows up in every photograph is that it all comes from one tiny culture. These systems work on the vessel's working deck, where flexible pipes and cables are deployed and recovered. One design uses a 50-ton 4-track tensioner, with 2 opening tracks allowing flexible pipes to be loaded from the side as well as from above instead of threading them through the machine. The unit fits inside standard shipping containers and can be configured for different load requirements. Sometimes the smartest engineering is simply removing an awkward step everyone used to accept. A floating production unit doesn't get to come home often, and when it does, the visit costs millions. The GTA FPSO arrived under tow for a full mooring system retrofit. Old anchor brackets came off in pieces. Inside the workshops, crews cleaned, welded, and painted the red replacement brackets. Outside, self-propelled trailers carried the finished assemblies to the hull, where shipyard cranes positioned each one to the millimeter. 20 years of holding station at sea begins with people fitting steel together on a workshop floor. Nobody asks where these things come from. A platform stands in the ocean and people assume it arrived fully formed. It did not. Every beam and every weld begins inside a fabrication yard. CNC beam cutters, plasma plate cutting lines, and sub-assembly workshops prepare each component, with identification codes stenciled onto every piece before it moves on. Self-propelled transporters carry completed frames to the blasting and coating facility, ready for years in salt water. 2 crawler cranes then lift an entire deck level and lower it onto the module below, matching each leg to its load point. Long before a platform reaches the sea, it has already been assembled, checked, taken apart, moved, and assembled again. So how exactly does flat plate become a pipe? Thick plate feeds into massive rollers. Each pass tightens curve until steel closes into a cylinder. A frame unlocks, crane lifts the tube. It sits on rotator rollers while a welding column boom runs the seam inside at controlled speed. No hand holds steady that deep. Plasma, nozzle tracks the file. A fabrication yard sits inside a free trade zone, avoiding customs delays for incoming and outgoing equipment. A 20-ton overhead crane serves the workshop. CNC machines cut steel directly from engineering drawings. When cranes cannot reach a work area, IR rider rope access technicians take over. Every pipe spool that leaves this workshop carries a story in its welds. Angle grinder cleans the edge, TIG welding lays the bead. Each assembly gets an ISO 9001 stamp. Traceable, accountable, not negotiable on a structure underwater for decades. A crane pedestal holds the crane arm. Get it wrong and every lift becomes a problem. Plates flame cut rolled on a FACCN machine into cylinders. Welding boom runs internal seams, no hand torch reaches there. Manholes cut, reinforced. Final lift, 63-ton crane. Right before a crane ever sits on top. Not every piece built in a fabrication yard becomes part of the platform. Some machines are built to install the platform itself. Offshore installation systems include tensioners, winches, and reel drive units handling loads up to 800 tons with reels reaching 14 meters in diameter. Many tensioner systems and winches have already been built for offshore projects, with each one designed to a specific project brief rather than a standard size. A fabrication yard is not a workshop. It is a logistics chain compressed into one place. Some facilities span multiple sites, building jack-up rig components, offshore modules, renewable energy foundations, and precision-cut steel. Plates arrive, get laser cut, rolled, welded, lifted by cranes, moved to the quayside on self-propelled transporters, and loaded onto waiting vessels. One project leaves. The next is already taking its place. Most offshore structures begin their lives somewhere almost nobody outside the industry ever sees. Before any vessel heads offshore, something on a screen at a yard decided its exact dimensions. 3D modeling feeds CNC cutting, automated welding follows. Laser lines confirm tolerances. When a 1,000-ton topside lands on a jacket, What stops it smashing the connection points? Leg mating units, steel cans packed with horizontal and vertical elastomers. They absorb impact, lateral misalignment, and settlement loads after cyclic, depermation, and stream capacity tests. Nobody sees them. Almost everything offshore depends on them quietly. Once a jacket reaches seabed, it must be leveled and held before grout sets. Waves do not respect curing schedules. Hydraulic pile grippers clamp each pile, locking position up to 200-inch diameter and 4,500-ton capacity, ROV operable by hot stab, 100% factory tested. The entire operation waits for one thing: the grout becoming stronger than the sea trying to move it. An offshore structure is never truly finished. It just enters a different phase of its life. A 200-ton blowout preventer stack is lifted off the drilling vessel, and a 180-ton replacement is lowered into place. On the West Jupiter drillship in Tenerife, the entire replacement took one working day. Old stack to the yard, new stack bolted down, vessel sails again. The rule in offshore repair is simple. You cannot always bring the structure to the machine, so you bring the machine to the structure. A dredger came into Hidromar with a failed draghead gantry. The repair team mounted a Mechanica WS2 boring unit directly onto the damaged trunnion, machined the bore to tolerance in place, welded reinforcement, then installed new large bore pipe sections. Downtime measured in days, not weeks. A pneumatic fender absorbs the impact when a vessel hits a structure. Before it does that job in open water, it does it in a press. IRM's DPN 25B Y4M fender compressed to 60% deflection under hydraulic load, then released, fully recovered, no creep, no rupture. That is the only acceptable test result. A cell fender and a pneumatic fender protect the same thing, but absorb impact differently. The DC 2500 hour is solid rubber, tested to 52.5% deflection under hydraulic press, third-party witnessed. Released, full shape recovery. If it does not come back, it does not ship. You started this video looking at a platform in the middle of the ocean and thinking, how does that exist? Now you know. Everything in between is the part you never see. Beams get plasma cut at 2 in the morning. Modules stack under crawler cranes to the millimeter. Sail out, land on a prepared seabed, lock with grippers, settle on elastomers nobody notices, then keep getting repaired, upgraded, and eventually decommissioned. Starting the accounting for removal that almost never looked exciting during early approval meetings anyway. Every offshore structure is temporary, but the industry keeps building bigger ones. At what point does scale stop paying for itself? When steel gets heavier, or when installation becomes too complex to justify the next project? What's your view? Share your answer in the comments. Thanks for watching. Some of the most interesting engineering on the planet happens far from the cameras. We try to bring it back. See you next time. Take care.